There's a lot of people not yet. Okay, everyone. We just finished a very interesting conversation, which we will now abandon and talk only about math. Okay, so far in the year, when we've talked about parametrics, okay, we've talked about equations of this form generally, just a number plus a number times t, and then we go on to our y component, and it's the same deal. It's this structure. Feel free to write this or don't. This is kind of a review moment. So parametric equations that look like this have a specific graph that comes out, and this is the graph of a line, right? This is called parametric form of a line in space, okay? So this gives us, and this is what you're going to be tested on partly coming up on Wednesday, right? Things like this and planes. And so we've gotten used to the fact that these numbers right here kind of tell us a point that's on the line. And these numbers right here, well, how would you describe those?
Direction vector.
The direction vector, good. They tell us kind of like the x, y, and z change. Okay, good. Or we have another form. We can write it like this. We can write it as x, y, z. This is called like vector form. And then we write that point right here. And then we write that direction vector here, you know, direction vector times t. So the visual that you kind of are supposed to have in mind there, I'm going to do it in two space because it's just a little easier to draw. If we have a line that we're trying to describe parametrically like this, we're saying, let's pick a point on the line and take ourselves there. That's this vector, right? Now you could go here or there, right? You could go to all these different points on the line. So I'm going to draw you a bunch of different vectors that take us to the line. This is sometimes called, by the way, P plus TV form, where P is a vector and V is a vector. So this is like the position vector and that's the direction vector. So all the things that I just drew in red, those are all like potential P vectors, right? They get us to the line. Any questions yet? Okay. And then the V vector just tells us, well, let's describe direction kind of parallel to the line. Now remember, vectors don't inherently have position. So it would be fine if I drew this whole thing down here, right? And then we just get the idea that when you add P to it, that shifts it up here, right? So all of those blue vectors would be like direction vectors V, you know? And so you could think of every point on the line is just the resultant vector, couldn't you? Think of it like this, right? You go along P and then along some multiple of V, and that takes you to a point on the line, right? So this is like, it's both a point on the line and it is a sum of vectors, right? It's a point if you think of it as a point, but it's also a direction to get there. We travel along the position vector and then travel along the direction vector, and we're on the line. So that's kind of what I want you to think as we begin talking about space curves. This idea of a vector pointing to a location on the line. Okay, so we've done that. We've done those types of equations, and we've also done planes. And I just want to remind you of that equation so that you're clear on what we're not doing today. We're not doing an equation of a surface. This is the equation of a surface, and we learned lots of other surfaces so far, right? We're going to basically just modify this to make more interesting shapes, okay? So the surface stuff is going to stay on hold for a little bit. So now what we're going to do, now we just modify to make interesting shapes. All right, oops, interesting shapes. And by shapes, I mean curves, right? Like something that's like a path through space. So you could think of, you could think of like designing the path of a roller coaster, for instance, right? That would be like a parametric curve, right? A space curve, okay? That's kind of the application I'm thinking, right? Or if you're, I don't know, take a spacecraft you're designing or an aircraft you're designing, and you're going to talk about like how the certain wires or fiber optic cable or something moves through that aircraft. You design it like with parametric curves, maybe. Okay, those are the applications that kind of come to mind. Any questions right now? Okay, so let's see what a vector function is. So let's just define it, and then I'm going to ask you right away to come up with a certain shape. So a vector function is something of this form. R of t R of t equals x of t and y of t. And this is a vector function in R2. And of course, there's a 3D version. R of t equals x of t, y of t, and z of t. And that's in R3. So if you write that down, we'll talk about what's actually happening here. These three functions are all just real functions. They all just take a real number as an input and give a real number as an output. But because we have three real functions embedded in a vector, in fact, what a vector function does, what R does, is it takes a real number as an input and gives us a vector in R3 as an output, right? It takes a number, which is t, and it gives us a vector in either 3 space or 2 space. And what does that vector do? It points to a location on the curve, just like I was trying to get at up here, okay? But you realize that this is just a different way of representing parametrics, right? I want you to note that if you're writing this stuff down. It's just basically parametric. Okay? But we represent it like this so that we can do calculus with it, so that we can do curvature and tangent vector and normal vector and all the things that I just went through on this formula sheet. Okay? Questions? All right. So let me draw a picture of what I mean, and then I'll have you play around with an example. So here's a nice picture for kind of what we're doing. So this is in 3 space, x, y, and z. And I'll do my best to make a curve that looks like it's kind of going through space. So let's go kind of like this. And think of that, that's not really an intersection, so I'm going to erase part of it, okay? I'm going to erase, oh, that's not what I meant to do. Let's get a different eraser. There we go. So like that, okay? Suppose it's doing something like that. It's not really touching itself. That gives us that 3D sense. So we'll call this the curve C, and suppose it's parameterized so that it's traced out like this, because it doesn't only just have a curve, like it has an orientation to it too. Okay, and you've got this vector function R of t, and you know what it's made up of. It's made up of these 3 components, 1, 2, 3. And I want you to think of various points on that curve as being a vector. Like suppose this right here is the vector R of 1. Now remember, the time is kind of arbitrary. So like, where does it start? Where does it stop? I don't know. Maybe that's R0. Doesn't matter. Maybe that's R1. As you go further along, that'd be just R of something bigger than 1, right? Like maybe this point right there is R2. Okay? So when you think about, my goodness, I've been so depressed in Algebra 2 lately. My students do not know like how to do stuff like this. I'm really upset. Like, they don't know what that means. Like the pandemic really, it's bad, right? The pandemic messed with people. Like I have this on a test and people are like, what do you mean evaluate that? I'm like, plug in 3. Like, what do you mean? What do I mean? So just we're clear on what that means, right? Like,
wait, what does it mean again?
R of 1 means put 1 into the function and tell me the vector that's output, okay? Or R of 2 means put 2 into the function and tell me the vector that's the output. Okay? So, all right, so the curve, you kind of get this idea that the curve is formed by the tips of all these R of something vectors. Okay? But it's just a curve. So don't get all worried about the fact that they're vectors. What we're really interested in is the curve. We express them as vectors so that we can do calculus with it. Okay? That's the kind of the why behind this. Questions? Are you guys all busy looking up salaries? Just be honest. I'm okay with it. It's fascinating to me too. Every time the board packet comes out, I read it immediately. It's sometimes a long process. I mean, sometimes those documents are very lengthy, as you know. So yeah, it's fascinating stuff.
There's another 1,000-page document.
Right. My goodness.
We don't talk about that.
That's right. We don't talk about that. And since this is being recorded, we really don't talk about that, right? Okay. So let's talk about a helix. I bet you all have a sense of what a helix is from biology, right? We got the double helix, DNA, right? You know, and I don't know. You get the idea. So what I want you to do is try and design one. And I want you to design a helix by going to CalcPlot 3D. Okay? So everybody do it. Grab your computer, click on my link, go to CalcPlot 3D. I'm going to pause the recording so we can actually have some fun. Recording, don't say anything awkward now, please. All right, the helix equation, I just want to note it for us. This is one that's parallel to the z-axis. Cosine t, sine t, and t. Now, of course, you could change the period. You could change the radius by putting other numbers in there, right? But that's going to essentially give you a coil that goes around the z-axis. Okay, let's talk about some of the other features of this function, like the domain. The domain of a function like this is just the intersection of the individual domains. Okay, so in this case, the helix is boring because all the functions in them have a domain of all real numbers. So therefore, the domain of the function is all real numbers. We could talk about the limits. Limits are just done component by component. So if you wanted to find the limit of a vector function, you find the limit of the first one, the second one, and the third one. Something interesting may happen in there, like you might have to do L'Hopital's rule or something like that. But that's really not the focus of our work here. I just want you to know that that's a thing. We could talk about continuity. So with continuity, remember, it follows conditions like this. So R of t is continuous at some value t equals a if two things happen. One, the limit as t goes to a of R of t exists. And two, the limit as t goes to a of R of t equals R of a. Remember, the limit has to exist, and the limit has to equal the value of the function there. Those are two conditions that you were told at some point last year, and I wonder if they ring a bell at all. No? Okay. That's fine.
It has to be continuous and a little bit like...
So we're not talking about differentiability here.
Oh.
Yeah, we're just talking about being continuous. So it just means that the limit has to exist. So, for example, in a 2D sense, we can't have this happening. It can't go like that. Have an asymptote there and be doing that, right? It can't be approaching two different values from two different directions. And then it can't do this either.
Okay.
So in a space curve sense, just turn those into 3 space and you've got the same ideas, right?
Okay.
So that's not continuous, nor is that. I'm going to take those out of the notes because they look too sloppy. Okay, so that's that. Good. So I want to do the interesting stuff for me in this section is when we talk about intersections of surfaces, okay? So I want to talk about 2 surfaces. So this will be our first kind of real example. I want to talk about the surface x squared plus y squared equals 1, which we know is a cylinder parallel to the z-axis. Okay, and I want to talk about the plane y plus z equals 2. So the power of our CalcPlot 3D is we're going to have no trouble getting a visual of this. So let's go and do that, okay? So we're going to look at the cylinder parallel to the z-axis and the plane y plus z equals 2. And we are going to look at a sketch. Okay, so first I'm going to go, oh, I can't do it that way, can I? Because we need to have not solved for z, right? That's called an implicit surface, if y'all haven't figured that out yet. X squared plus y squared equals 1. That's our cylinder. And then I'm going to look at the other one I can solve for z, and it is z equals 2 minus y. Oh, I made a mistake, sorry. I want to keep that, and then I want to change this to, oh, that's fun. 2 minus y. There we go. Okay, so let's zoom out just a smidge so we can see this a little better. So basically, I want to parameterize. When I say parameterize, I mean find a vector function. I want to parameterize the intersection of this cylinder and this plane, so that when I uncheck these, I want to be able to see the curve that's formed by those intersections. You get the goal? Okay, this is a really easy one. Okay. Really easy. Here's how we do it. And I want you to kind of get used to some of our strategies here. The first one is when we see circular motion here, right? So this should be your tip off. We've got circular motion going on. So that means I'm going to right away parameterize so that that equation works out. I'm going to let x be cosine t. I'm going to let y be sine t. By doing that, it automatically satisfies this equation because of Pythagorean identity. And this is one of your two strategies, basically. One strategy is to notice that you have circular motion and therefore choose trig functions for two of your parameters. Okay? And then z is a simple case of substitution. Z is just 2 minus sine t. This thing is the parametric form of the vector function we're talking about. If I was really being picky and formal about this, I would say let's write it in this form, 2 minus sine t. That's our vector function. And now we're going to more easily be able to do calculus with it later on as we go through this unit. Okay, so let's try. Does it work? We'll go over to calc plot 3D. We'll see the curve and see that it's the intersection.
Is there a way to graph the intersection like in 2 dimensions, like on the plane that like intersects? You get what I'm saying?
No, I don't get what you mean. Sorry, I didn't mean to say no. I don't understand.
So I'm saying like, say you treat your XY coordinates as the plane that's like, going through.
Okay.
Is there a way that you can graph that intersection?
Oh, that's interesting. Man, I don't know. I bet you there is, but I don't know how to do it off the top of my head. Yeah, so let's try and do this space curve. So we have cosine t, sine t, and then this one's going to be 2 minus sine t. And let's turn it on and see what it looks like. Okay, that's not showing up real well. So I'm going to say use constant primary color. Does that work? Ah, there we go. Check it out. So that thing looks like it's right. And when I make the cylinder and the plane disappear, we should just see this kind of cool slanted ellipse. So I'm going to turn those two off. And we see, yep, there's our slanted ellipse. Okay, I think that's pretty neat, right? I mean, finding the intersection of two surfaces, anything you design in engineering is doing something like this, right? This table, right? You've got a surface, you've got a surface. This mouse, it's kind of an interesting surface. You're going to blend the intersection of this surface and this one. Or in real life, I had a friend years ago who was designing cell phones for Motorola. Back when Motorola was in our area, he lived up by me. He went to work for Google and probably makes the kind of money we were joking about earlier, like $400,000, something like that. One sec. And he talked to me about this real work. When I was sharing with him what I was teaching you guys in this class, it was like, yeah, we do that. We do that kind of thing where we look at how surfaces intersect. So it's kind of cool.
Are we gonna ever do like the math behind like tracing a 2D shape on that curve?
Tracing a 2D shape on that curve. I'm not sure what you mean.
I don't know what the word for it is. So like if you have a circle, like making a circle extrude on that path.
Oh, yes. But that involves a whole nother parameter, right? Because now here's what we need to do. What you're asking is take a circle that, you mean like a circle that goes around that curve?
Right, and then make
And extrude it around?
Yeah.
Yeah, but those are called parametric surfaces. And that's where we would involve a t parameter and a u parameter. It's not for a long time though.
Okay.
Yeah, but it's coming later.
Yeah.
Other questions?
I mean, it sounds cool. But like,
Okay.
it sounds pretty hard.
Yeah, no, that is a really hard section on parametric surfaces. Yeah. Okay, so there's other ones that are like a lot easier. Like here, that one is pretty easy on its own. But here's one that's even easier. Suppose you've got the surface z equals x to the third, and the surface y equals x squared. It's a cool picture, but the parameterization is extremely easy. Okay, let's parameterize it before we go to the picture. So in this case, we can just let r of t be, here we go, t squared, and t to the third. Simple substitution, right? So there's another strategy that you want to keep in mind. Just like, I don't know how much you remember pre-calc, but if you're trying to parameterize like x squared minus 3, and when you first learned how to do parametric equations, we were often just told like, well, let x be t, let y be t squared minus 3. That's in effect what we're doing here. We're just choosing one of our variables to be t. In this case, it was simple to use x. And the rest of it comes through substitution. So let's go see what it looks like. So these are the two main strategies, you guys. Look for circular motion. That's one. And then just let a variable be t. Okay? All right. So let's talk about, can they be solved? Yeah, z equals x to the third. Let's look at that one. Cool, right? You know what that is? What is this called? Yeah, good job. It's called a cylinder. You've taken a curve and you've extruded it through space. Good. And then this one was y equals x squared. This is also going to be a cylinder, right? So we've got this thing. All right, let me hide this curve so we're not seeing it anymore. So the intersection between these two surfaces has got to do some kind of little bendy thing where it like comes in here but then curves around kind of the other way, right? So let's see if our curve does it. It should. X is t, y is t squared, and z is t to the third. And we let that show up, and we kind of hide those, and that's what the curve does. Isn't that crazy looking? So that's the intersection of those two surfaces.
Wait, if you look at it from z, it looks like t squared. Yeah.
Yes.
Wow, that's crazy.
Sorry.
Wow.
I bet you there's a shortcut that would allow me to look directly on it from.
I think if you press restrict view to 2D.
Oh, really? Are you right? Oh, yeah. Thank you. Very nice.
I did it on accident. No, I don't. And then I unchecked the box and I didn't know how to.
Thank you. That's really helpful. Hey, by the way, if you guys are exploring and you find something like that, please share it with me because I'm kind of a novice with this program. I mean, I imagine it's more powerful than I know. But yeah, if you find stuff like that, let me know. Great. Okay, so let's do another one that's maybe a smidge more interesting. So this time I'm going to let you do the work on your own. So I would like you to take two surfaces. The first one is a semi-ellipsoid. So x squared over 12 plus y squared over 24. Here's a little review for the exam next time. This is an ellipsoid. We all agree? Right? You got all the variables being squared. There's all addition, okay? So we've got an ellipsoid, and I'm going to say it's a semi-ellipsoid because I'm going to make this restriction on it. I want us to talk about when z is greater than or equal to 0. Okay? So here's your goal. I'm going to have you intersect that with the surface y equals x squared, which is a parabolic cylinder. Okay? Your task is to come up with a vector function that does this, x, y, and z. And I also want you to tell me what are the limits on t that will actually trace it out properly. So that's one thing I haven't really addressed yet, is that if you've got a closed curve, we should talk about the low t and the high t, which defines that. Okay? And I have one slightly funny, but maybe not best to say on a video joke about that. Okay, so the recording is now on. So going back to here, there's my x, there's my y, there's my z. And then what I did was I said, well, when do we touch the plane z equals 0? So I said, let's let this thing be 0. I solved this quartic equation, but it's really just quadratic looking, by factoring and found that t squared is 4. So that leads me to my bounds on t, -2 to 2. That's what allows us to go from that bottom, come up, and then come around back to the bottom. Okay, that's that. Questions? Questions from the people who are here, because the people who are not here, I would have to start over from scratch. Yeah. We've actually had kind of a fun block. We've been talking about a lot of off-task things. So, yeah, we were talking about teacher salaries and whatnot. It's interesting.
Isn't that supposed to be negative 24?
Negative what?
Negative 24?
Negative 24. Yes, good catch. That should be negative 24. Sorry, what's up? That and this. There you go. Okay. Does the group that's been here kind of feel like they get what's happening? Do you have anything you want to ask? Yeah.
So you just set a variable equal like x, y, or z equal to t.
Yeah.
Solve for everything.
Yeah. Exactly. Like using reasonable substitution. Yeah.
I remember on the homework there was a problem. This was a little bit ago, where two planes intersect, and you had to find a plane that goes through a line of their intersection, but also goes to a certain point. Could you set the two planes equal to each other, parameterize a variable, and then solve it that way?
Well, the trouble is you can't really parameterize a plane. Oh, wait a second. I think I understand what you're asking. You mean like use these techniques to find the intersection of two planes?
Yeah, just set the two planes equal to each other, let x, y, z equal t, then solve a system for x and y. Did it let you, like, have
I
all
think
the-
so. I think so. We'd have to play with it. That sounds right. Yeah.
I guess I'm just a little confused. We were given one cylinder, one conic, like,
Yeah. You were given those two. A quadric surface.
quadric surface.
Yeah.
What was like our goal?
The goal, yeah, I'm sorry. I didn't state the problem well, did I? The goal was find the curve of intersection. That's important to have noted. Yeah, the goal is to find the curve of intersection. Okay? Yes, Eric.
So the two curves you wanted to intersect were the
Surfaces.
Oh,
Yeah, the ellipsoid and this thing, which I know this thing looks like it's a curve, but not if we're doing in free space. It's actually a cylinder, right? It's a parabola extruded through space.
right.
Okay. Other questions? Okay, let's do another now where I don't let you just play. I'm going to guide it through for the people who weren't here. Okay, so here we go. We'll do one more of these intersection problems. All right, so I want you to find the vector equation, or sorry, not equation, vector function. Find the vector function for the curve of intersection of, oh, here's a little review for our test next class. Do we remember what that surface is called? Saddle, good job. The hyperbolic paraboloid. So we're going to have the intersection of the hyperbolic paraboloid. Yes, the Pringle. Good. Hyperbolic paraboloid. When you say the confusing one, though, I don't think any of them are that clear. So
Wait, how do you know?
Like, this is
No,
the
this is like
hyperbolic.
the weirdest one.
Yeah,
How do you know
this
it's
is like the
hyperbolic?
like they're all
okay, sure. There's two kinds of paraboloids. The hyperbolic, which is when we see x squared minus y squared, and the elliptic, which is when we see x squared plus y squared. Those are the two kinds of paraboloids. The others are all hyperboloids. There's the hyperboloid of one sheet, the hyperboloid of two sheets, and then the elliptic cone, which is kind of like a degenerate hyperboloid. Because it looks like that crisscross, but it's the cone, you know? Okay? All right, so I have one surface. Remember, this is a surface. Shh, come on, come back. And the cylinder, x squared plus y squared equals 1. So let's go take a look at the picture of the saddle intersecting the cylinder, and then we will create the vector function for the intersection. All right, so we're going to go z equals x squared minus y squared. Should have that one show up. Very cool. Okay. Now we'll dump that one, and then let's take a look at this one. This is x squared plus y squared equals 1. So we'll take a look at that. Okay, so there's the cylinder going through the middle of the saddle. Okay, and we're going to try and design the curve that starts here and goes around here and then goes back on the other side. It's really easy, actually. Okay, so that's the picture. Now here, actually, I can just do this. Why don't I copy and paste this picture into our notes so you have it if you look online. All right, so we'll snip this. And there we go. And I'll paste that over. These poor people who taught this course 20 years ago. That was a rough time to sketch these. Okay, so what we're going to do is we notice right away that we have circular motion here, right? So instead of, sorry, not a highlighter. Instead of choosing x to be t, we're going to choose x to be cosine t and y to be sine t. Now don't forget, you can totally do other cylinders by putting a constant in front of here, right? You could even make it an elliptic cylinder, right? If you put a constant in front of one and a different constant in front of another. We could easily make this have a radius of whatever we want by just adjusting the constants in front of here. Now, z equals cosine squared t minus sine squared t. And the observant among you will notice that this is an identity for cosine 2t. Okay, so here's our vector function. R of t equals cosine t sine t and cosine 2t. And because we're just wanting to go around this thing once, we can say 0 less than or equal to t less than or equal to 2 pi. Now, like I said, this seems unnecessarily complex today because we're just like, well, couldn't you just use like parametrics here? X equals y equals z equals. The goal is to do calculus with this later on, to do tangent vector, normal vector, curvature, all the other interesting things we could analyze about this curve. See, this class takes shape very slowly, doesn't it? It's like we haven't really done any calculus yet. I first have to get you thinking about 3D. Then I have to get us to analyze curves in 3D. Then finally we analyze surfaces in 3D, which is where we really do partial derivatives and multiple integration. Okay? So stay with me if you're feeling like, where's the calculus? It's coming. Yeah.
Why is t limited to 0?
It's not, but those limits will make us do one time around. You could let t be anything and we'd still have the curve. Okay, so let's do it. If I let this thing be cosine t, and the next one be sine t, and the next one be cosine of 2t, I'm going to let t vary from 0 to 2 pi, and then show it. Yay, it looks like it worked, but I'm going to need to change or get rid of the other surfaces to see it. So there's our surface.
That's even more like
Yeah, that does look more Pringle-like, yeah. You're right. Yeah. You would need to etch out the inside so you could actually see it. Okay? And then look, the 2D thing is kind of cool too, isn't it? Look, you got a circle on there. I just wish we could see it on the other axes, and I don't know of a way to do that. Like it's only showing us looking at the XY. Rotate it here, you think? Let's try it. So if I look along the Y, and then restrict to 2D? No.
What if you try to rotate it?
What about this 3D mode? Does this do anything for it?
What if you try to rotate it when it's 2D?
Oh, that's a good idea.
So for our purposes.
No, not working. What if I put the surface in there? Ooh! Now that's really neat because this is actually showing you something we're going to learn later about level curves. Ooh, look at what it did. Did you guys see that? It like polygoned it up when I showed the cylinder. Polygoned it up, yeah. It's like it's trying to show that there's another surface in there that we're just only seeing it kind of coming out toward us. But if we go back to the non 2D, go back to this, now we can see it. Man, whatever person made this and just made it free, good for them. That's cool. So, what's the root of this website? Something at libretext.org.
That's the text.
Maybe.
Oh, yeah.
Oh, is it really?
Yeah.
Uh-oh, so hopefully I'm not doing something criminal.
I use that all the time.
We're recording. Be careful. Go ahead. Shh. Let me hear.
This one now is the best, like the smart function, but is there a reason why we make X cosine?
Is there a reason we made X what?
Cosine.
Cosine? It's just because I'm trying to parameterize a circle with this curve. You could have let X be sine and let Y be cosine because we don't really care about where it starts and stops.
I feel you, Ralph.
Yeah. Okay. I think I've reached the end of my notes. Yes, I have on that. Let me look one other place. Done with that. Okay, so now I want to just play with some problems all together, and we'll just try a few more, okay? So did everybody get the review sheet? This is the Chapter 13 review. So we're just going to play with these until we learn everything on here, okay? So we'll do our usual throw out a question to a random person. Okay. Oh, yeah. Yeah? Yes. Wait, I can't hear Joshua. Listen, please. Yeah. The rest of them would just be ugly, but yes. It would still parameterize it. Mm-hmm. You might have to be more creative then about the bounds that you put on t, right? You might have to do a little more work to figure out, it's probably not going to be 0 to 2 pi, right? because you haven't parameterized a circle. You haven't done the unit circle. Yeah. Okay. All right. So question number 1 on the concept check. Here we go. Someone who is actually here. Let's go with Sanjeev. You weren't here. Never mind. Jessica wasn't either. Josh was not either. Keenan wasn't either. Jaden was. Okay. So Jaden, what is a vector function? We're doing concept check question number 1. What is a vector function?
It's like the way you express the curve.
So it gives you like a curve in 3 space. And what about just the technicalities of writing it? We have what we're using this notation of what?
Like the position.
Yes, it's like a position. It's a position vector basically, right? So it's this R of t, and there's 3 components in it. There's 3 functions that are all real functions. They could be anything. They can be linear. If they're all linear, then you just get a boring line in space. Okay, good. All right, how do you find its derivative? This will be fun because now we can preview stuff that we don't know yet, but we'll be ready for it when it comes. So how do you find its derivative? Let's send that question to James. We haven't learned it yet, so you're just guessing. What do you think we do? Take it by components. He's exactly right. So there, I just taught you another lesson with one question. You do x prime, you do y prime, you do z prime. That's how you find a derivative. By doing that, you've essentially found a tangent vector. Okay, good, James. All right, how do you find its integral? We'll say Nathan on that one. What do you think? By parts again. You just do integral of x of t, integral of y of t, and integral of z of t. Now, what's interesting is that for these, there's like kind of a physical representation. This is a position, this is a velocity, which is a tangent vector. This one, I can't say like, oh, this is like the area under the curve. It's not. All that it helps us do is go from acceleration back to velocity, back to position. You get what I mean? Like if I gave you acceleration, we could take an integral to find velocity, take an integral to find position. Okay? So we'll learn that soon, but we really basically just learned it. Okay, Reva. Where is Reva? Over there today. Okay, Reva, question 2. I know. So what is the connection between vector functions and space curves? What's your idea? As of your understanding of right now, what would you say? This is kind of fun to ask people who didn't hear the lesson what their thoughts are. No, seriously, because it gets kind of at like the really conceptual meaning behind it. What would you say the answer to that is? Yeah, the vector function defines a space curve. What it does is it basically, so all of the R of whatevers, they are just vectors that point to the space curve. They point to various points on the space curve. For those of you who are going to go back and watch the video, you're going to come across this picture right there where I kind of tried to explain that. Okay, the curve is formed by the tips of all of those vectors. Good. Okay, that's number 2. Let's see if we can keep going to number 3, or maybe we can't do any more at this point. How do you find the tangent vector to a smooth curve at a point? How do you find the tangent line, the unit tangent vector? Jaron, what do you think? No, sorry, you were. How do you find the tangent vector to a smooth curve? You do. It's just r prime. Isn't this fairly intuitive? It's almost like I don't need to teach you all of these things. How do you find a tangent vector? You find a derivative.
For the definition of a smooth curve, is it something that the first square plus the second square equals to something? What is the definition for
a smooth curve? A smooth space curve is, let me see if I remember it off the top of my head. It has to have a continuously turning tangent vector, which means that r prime cannot have any cusps or corners.
Right. I found that on my real analysis test, but if I remember it correct, it's something that if it's written in the parametric form, that st squared plus yt squared equals to 1, that's not equals to 0, or something similar.
Yes, I believe you're right.
Right.
That neither derivative can equal 0 at the same time. That's I think the formal way of describing what I said. You have to have a tangent vector that's continuously turning, but the meaning of that is that r prime, so something is smooth when r prime of t does not equal the 0 vector, which is what you're saying, that this component can't be 0 at the same time that component is 0. Does that make sense?
Oh, I
You
see.
confirm?
Yes.
Okay. You've read ahead or just familiar with this? Okay. Intuition?
So is it essentially the 3D equivalent of differentiability?
Yes. Yeah.
Yeah, absolutely.
And did you hear what I just said about a continuously turning tangent vector? That's something that's going to come up. I need to find a space curve. Does anyone have a chord on them? Let's see. We can just use. No, not a musical chord. Silly head. Okay, here we go. This will work. Okay, so this is kind of cool. So if you take a helix, right, I'm going to define like a kind of a tight helix here. Curvature, you know, on your formula sheet it says K. There's those complicated formulas for curvature. Well, those are a measure of how fast the tangent vector is turning. Okay, if you've got something like this, okay, the tangent vector is like this, and it's turning, however so slightly, right? But if I curl it in a lot, right, then in that same time increment, the tangent vector is going to turn a lot, right? And so that's a lot of curvature is a lot of rate of change of the tangent vector. But what is rate of change of the tangent vector? Second derivative, right? So there's some interesting stuff there, right? The curvature is related to that. Whereas if I have a very slight curvature, the tangent vector is not going to change very fast at all. But what's crazy is we have to redefine the curve to be in terms of not t anymore, but in terms of arc length. So we have to say for a given length of curve, how fast does the tangent vector turn? Okay, yeah.
So you said the derivatives is continuous.
Yes.
Oh, and that if it's not continuous, the second derivative can still exist, right?
Say that again.
If the first what? No, it doesn't make sense.
Okay.
Right. Yeah. Yeah. I know.
Okay. All right. That's done. Okay, so we'll leave it at 3. I don't think we can do anything beyond 3 at this point. Okay. All right. Let's go to 1. Go ahead.
Just out of curiosity, for 5,
Yeah.
would it be the integral from whatever points you want to like do it, square root of the derivative of each component squared?
Yes. Exactly. Good extension from single variable. Okay. True, false. Question number 1. Let's ask Matt. Okay. The curve with vector equation r of t equals t cubed plus 2t cubed plus 3t cubed is a line. Why do you say that's false?
Because it has there's the third power to the curve.
That's my gut instinct too, but look what we can do.
Oh, it cancels. So yeah.
That vector function can really be written like that. So this vector function just represents all scalar multiples of 1, 2, 3, right? This is literally a line through the origin and the point 1, 2, 3. Isn't that tricky? So this is actually true. This is a line, okay? We can look at it on CalcPlot 3D, and it should show us the same thing. So our first component was space curve. What was it? T cubed. And then what? 2t cubed, and then 3t cubed? 3t cubed. Okay, let's hide that curve, that surface, and show this curve. See? That's a line. Cool, right? That's very counterintuitive. Okay, number 2. The curve. Now, you guys can just be guessing on these. I know that we could just go to technology and see it, but let's try and figure it out. So the curve r of t equals 2t, 3 minus t, 0. Oops, I just wrote down number 3. Okay, we'll pretend we're going on to number 3. Number 3, that curve is a line that passes through the origin. Let's talk to Kristen. What do you think? False? Let's write it parametrically. I think you're right. X equals 2t, y equals 3 minus t, z equals 0. So it contains the point 0, 3, 0, and there is no way to make all three coordinates 0 when t is a constant. So you're right. False. This is not through the origin. It's a line through the point 0, 3, 0. Good? Okay. Let's do 2 then. Let's back up to 2. Okay, so 2 says, take the space curve r of t equals 0, t squared, and 4t. Is it a parabola? Let's go with Peter. What's your intuition, Peter? Where's Peter sitting today? Right there.
True.
You think it's true? I think you're right too, but I got to prove it to myself.
It's like a parabolic
This
In the YZ plane, right?
Z is increasing linearly and Y is increasing.
Like, check out if we wrote it like this. Y equals t squared, z equals 4t, and therefore t equals z over 4. So y equals z over 4 squared. That is the equation of a parabola, just not in the plane that we're used to, right? So that's true. Good job, Peter.
So like this is the x. It's like this, but it's just extruded this way.
No, it's actually literally a curve, right? Because look how x is set to be 0. X is constant at 0. So if I let x be 0 and y be t squared and z be 4t, it looks like this. It's literally a parabola. Yeah. Wait, let's zoom out. There we go. See? And it's a parabola actually that kind of opens to the side, right? Because the dependent variable z is not the one that's alone. We're with a power of 1. In this case, y has a power of 1. Is that okay? All right, good. Who talked there? That was Peter. Are we okay? Questions? What's our time? 11 minutes? Okay. All right, good. Okay, number 4 in the true-false. This says the derivative of a vector function is obtained by differentiating each component function. Gretchen. No, she's truly not here. She's like not here. Nick, what do you think? True or false? The derivative of a vector function is obtained by differentiating each component function. Yeah. We didn't learn it formally today, but it's true. Good. We're going to stop there on the true-false, okay? We'll go on to the actual exercises, okay? Let's do one on the back. All right. Sketch the curve with vector function t cosine pi t and sine pi t when t is greater than 0. Let's ask someone who is here. Amanda, what do you think that looks like? We could, sure. It would look like this. So r of t equals t cosine pi t sine pi t, and that's the whole thing. Good job. And what axis is it parallel to? Good job. Parallel to x. Because we've got that circular motion in the YZ plane, and then it starts coming out toward us while it's turning. Okay? All right, just for fun now. We haven't learned this yet. Let's do B. Okay? So someone's going to have to walk me through the derivative. R prime of t. Hamza, is he here? No. So Hamza and Gretchen are actually absent. Are they the only two actually absent? We should have 3 missing seats then. 1 missing seat, 2, 3. Yeah, okay, so they're the only 2 that are gone. Okay, Eric, can you take the derivative of each component for me?
Okay, so that would just do the x would be 1, and then negative sine of pi t over pi.
Nope, times pi.
Times pi.
Yep,
Right.
that's the product, or the chain rule.
And then it's the pi cosine of pi t.
Good job. Pi cosine of pi t. Good job. Okay, so tell me about if we were to sketch that curve, oops, parentheses. Well, you don't have to do this. Anybody can do this. What would that look like? Yeah?
It would be a circle
Good.
with the x coordinate.
Yeah, perfect. So it'd just be a circle sitting out a little closer to us, right? That circle would have a radius of pi, and it would be out at an x of 1. Good. Okay, second derivative now. Ivan, can you do that one?
Would that just be 0
Yep.
pi squared cosine pi t?
Good job.
Then pi squared, negative pi squared
Yeah.
sine
Nicely done. So let's see, what would that be? Another circle, right? But it would lie where? Yeah, where x equals 0. It's going to lie in the yz plane. Yeah, good. Okay, 1 is done. 2. Okay, good. This is a domain question. I never did an example of this for us. I wanted to have you see this at least once. All right, the question says, let r of t equal the function root 2 minus t, e to the t minus 1 over t, and natural log of t plus 1. Oh boy, algebra 2 coming at you here. Ready? Josh Sorkin. You weren't here, but that's okay. You took algebra 2, right? You did. Okay, great. Okay, Josh, what's the domain of the square root of 2 minus t? T must be, yeah, so t must actually be less than or equal to 2, right? Because if t were 3, we'd have a imaginary number there. Okay, so there's our domain of the first component. Good. Okay, and Jacob, what's the domain of the second component? Nope, t cannot equal 0. Good job. And Chris, what's the domain of the last component? Feel free to walk me through it. You don't have to know it off the top of your head. T plus 1 must be greater than 0. Remember log functions? They look like this, right? So all of the inside that's called the argument must be greater than 0. So t must be greater than -1. Now let's put all these ideas together to get one domain of R, okay? So on a number line, we've got everything that is less than or equal to 2. So that's this and everything below. But t cannot equal 0, so 0's out. And t must be greater than -1. So here's -1, and it must be greater than, so this way. So the intersection would be, in interval notation, we would say -1 to 0, union 0 to 2. Such a great algebra 2 question embedded in a calculus question, right? There's no calculus there at all. It's just domain and range, basically. So, or actually, we didn't talk about range, but it's domain. Good? All right, now we can do a limit question. Ready? I was tutoring someone for their limit test the other day. It was kind of a challenge, actually. All right, so we're going to take the limit as t goes to 0 of the square root of 2 minus t. Well, that's an easy one. Sub in 0, we all okay with that, right? We just get root 2. Let's take the limit as t goes to 0 of e to the t minus 1 over t. Shall we lope it? Right? Because we do get 0 over 0, don't we? So let's lope it. Okay. That's the limit as t goes to 0 of e to the t over 1. Do we have to lope it more? Nope, we're done. So that's 1. Very good. Wait. Yes, all calculus teachers have their own silly way of saying that, so that's all good. Okay, and then the last one, is that an easy one? Yeah, as t goes to 0, the last one is the limit as t goes to 0 of the natural log of t plus 1. And that gives us the natural log of 1, which is 0. So this means that our actual limit answer is a vector. Root 2, 1, 0. That's our answer. We have time for one more or so. Ooh, yes, this will be fun. Make someone do a derivative. Part C, r prime of t. Who's next? Chris just went. Joe.
Okay. So I guess r prime of t would be the x component would be -1 over root 2 minus. Oh yeah, -1 over 2 root 2 minus t.
Wait, where do you want your 2? Do you want your 2 up top or on the bottom?
On the bottom.
On the bottom. Okay, thank you. So 2 is down here. Did he get that right? Let me do that quick in my head. Yeah, that's good. Okay.
The next one would be just e to the t. Oh, is that divided by t? Okay.
Yeah, it's about. So wait, do we have to do quotient rule then?
Yeah.
Oh, that sucks. Let's remember it. Okay, so it's f prime g minus f g prime all over g prime, right? No, just g squared. Okay, so what's f prime then?
So f prime is going to be
E to the t, good. What's g?
Yeah,
Times t.
e to the t minus 1.
Yeah,
Times 1.
yeah.
The divided by.
Wait. Is it times 1? Yeah, times 1. Divided by,
E to the t minus 1 over t squared.
no, just t squared.
Oh, sorry, yeah, t squared.
Yeah, g squared. Okay. Oh, that's a fun one to remember, isn't it? Okay. And then the last one,
The last one was
1 over t plus 1. Good job. Okay, so that, now here's what we're going to allow. Because I trust that you passed calculus, here's what we're going to do. Look, we're going to get to define functions on the calculator. Look at this. This will be something useful for you to know. I'm going to define a function as a vector full of expressions. So I'm going to define it in this case as, let's see, square root of 2 minus t, e to the t, where's my thing? E to the t, oops, not control, crap. E to the t minus 1 all over t, right?
Yeah.
And then that's the bottom one, natural log, t plus 1. Okay, so once it's defined, look what we can do now. This is great. Shift minus, d dt of r of t, done. Right? So quick, really, yeah, define. It's this little button next to the 9. Do you see it? The colon equals thing. Okay. Yeah, you can, or you can just do menu 1 is real nice. Yeah, store something, right? When you do that.
And it just takes, you write what you want and then say control bar.
Yeah, exactly. So listen, I want you to be flexible with the calculator because you're going to be using that on the next exam. I don't mean the one that's coming on Wednesday. Okay? All right, last thing to say and then I'll stop. When you walk in on Wednesday, I want to get right to the exam. So we're no messing around. I want to give you maximum time. Okay? Dividers will be up. I'll get here early. And as soon as you walk in, you can do it. Okay? Thanks, everyone. You get to keep those. Everyone has their own copy now.